Hey everybody, just wanted to make another quick video. This one's going to be talking about skeletal meshes versus static meshes and the performance and when you should be using one or the other. The most common misconception I see in especially the indie game space, is that just because an object is animated, that it should have to use a skeletal mesh and that it should need to be rigged with bones. A common example of that might be, for example, here we have, a pistol, a gun in a game. Most games, most assets you see on the Unreal Marketplace or online, they're rigged skeletons where you've got a bone for your slide, you've got a bone for your trigger, and a bone for your hammer, and a bone for your magazine. However, I think that in a lot of cases, this sort of technique is a mistake, and it's going to be costing performance. And there's other situations as well, like, for example, maybe you have a chest or a box that can open and close. A lot of people might put a bone in that so that the mesh can hinge, right? They think, okay, well, this needs to be able to move, so I'm going to weigh these vertices to a bone, and that'll allow me to move it. I can use a skeletal animation. The mistake there is that you can animate static objects through the Vertex shader, and there's a lot of different techniques that you can use to achieve that. I'm going to be talking broadly about several of them. But these skeletal meshes are going to have a greater per vertex cost every frame. They're going to be ticking every frame. They're going to be generally not able to be instanced at all or as easily. They are going to be more expensive per vertex. So they're going to be more expensive per bone than a static mesh, which doesn't have any. So I think that I really just want to challenge you to ask yourself more questions when you go to create this asset, and not just say, okay, does this need to be animated, but also, is there a way that animation can be achieved through the Vertex shader? Does the physics asset need to change with this animation, right? If you have a human character that's up close and has a hitbox, maybe again, if we look at a shooter example, you're shooting at an enemy character and you need that bullet to have impact with a hitbox, and that hitbox needs to follow the physical representation of that character, then you don't want to do that in the Vertex shader, because the Vertex shader isn't going to change the physics asset. That needs to be a skeletal mesh. Now, crowds and distant characters, or maybe small animals like frogs and birds and things like that, they don't necessarily need to have their physical asset represented perfectly by the mesh. These are generally small visual details that don't have significant gameplay implications, right? The slide or the hammer or the trigger moving on a gun as part of an animation doesn't really impact the way that that object physically interacts with the game. It's just a visual effect. So I'm going to hop over into Unreal Engine real quick, where I have this loaded up with a material. And what we can see here is if I, for example, turn this on, you can see that this trigger is being animated. And this is a static mesh. This is entirely being animated through the Vertex shader, right? I can go in and I can make the hammer animate. And I can go in and I can make the slide animate. You can change the magnitude of these animations. Right now, it's only moving a little. Now it's not moving at all. And so the point I'm making here is just that this is going to be significantly more performant, right? I can have a much greater number of these assets in a scene. They can have more complex animations and much more detail than they would necessarily be able to have at the same performance level than if they were skeletal. And you can actually test this, right? You can actually look at the millisecond cost of the animated meshes in a scene. And, and it depends on, again, how many you have and so on. But if we go ahead and I'm just going to bring in a skeletal version of the same mesh. So this is the same mesh. This is just a skeletal version. And we are going to turn on our stat anim here. And I am just going to quickly simulate this. So you can see there we got skin mesh comp tick here of 0.03 milliseconds, and that's really not a lot, right? But the main thing is that that these add up, right? And that's just one piece of the animation cost. And the more you have as far as objects in a scene that are doing this, and this may be a skeletal mesh, but it still doesn't have any bones in it. It just imported it without any bones, which is going to make it less expensive, right? But if we get rid of this, we bring back this one, you can see here that is 0 milliseconds, right? So essentially, from a CPU standpoint, that's going to be significantly more performant than a skeletal mesh would be. And there's no loss in visual quality. You can get this to animate in exactly the same way as a skeletal mesh would. So if we go back to Blender, the way that this is working here is I've got each element of this mesh, such as the slide, the barrel, the trigger. You can see that each of these elements are their own separate island, and that's because I don't want the polygons connecting, right? If the polygons of the slide were connected to the polygons of the frame, then as the slide moved, I grab this and I move it, you don't want the polygons of the frame to be moving with it, right? You want them to be free. And you could do this by making them separate meshes. But in this case, I've chosen to just make them separate islands within the same mesh. So the next thing I've done here is actually to give them different vertex colors. So if we go over into the vertex colors here, you can see, okay, here we go. You can see that each element, the slide, the hammer, and this is all in the alpha channel, so it's grayscale, so it might be a little hard to see the difference. It's pretty obvious with the slide versus the frame and the barrel, but these have different values. So I've given the slide a value of a 1, and maybe the trigger is 0.75, the hammer is 0.5, right? So they have different alpha values that allow me to basically use the vertex color to identify elements of the mesh within the vertex shader. So I can say every vertex with a value of 1 on its alpha channel is going to receive a certain vertex transformation. And so within Unreal, what this looks like, if we go to the material, there's a lot going on here, but the simplest thing is going to be a linear transform. All right, so if we look at this material, what we've got is the vertex color node, right? And I'm taking the alpha channel and I'm putting that into a bit mask. And the bit mask essentially allows you to search for a specific value and mask out all other values of data. And in this particular case, that value that I'm using is 0.003922. And the reason for that is because the bit mask is expecting a value, a grayscale value between 0 and 255. But Blender is taking that value as between 0 to 1. So I think with this that was maybe a 1, and I divided that by 255. I'm not going to redo the math here, but essentially you take the value that you've mapped your mask to, and then you want to make sure that it's written in a way that Unreal is going to understand it. So this is essentially masking out anything that doesn't have that value. So what I can do here is show you that mask. If we take this result and we pop that into our base color, you can see that the slide turns white, everything else is black, because that value is being masked. And if I were to do the same thing here with the hammer, and it's just using a different factor, I think, this one might have been, 0.5 in Blender. You can see that the hammer gets colored white while everything else gets colored black. So that's what that's doing, and that just allows you to isolate different parts of the mesh. There's other ways you could do this. You could, for example, use the RGB values to store information about the group. Like, let's say, for example, what we really want to do with this slide is get it to move along the x-axis, which is what the rest of this code is here for, right? So if I look at this, we take our mask and we're multiplying it by a vector in order to get the polygons to move along that vector. So that vector here is just red, right? Just 1 in the red channel, or the X, 0 in the green or blue. And so what that's essentially going to do is make the slide move along the frame, because that just happens to be the X direction. And then we multiply that, our 1, 0, 0, our vector, by the magnitude, the strength that we want that effect to have, right? So here I've just got a sine wave that's being multiplied by a parameter. So that tells me, the parameter is essentially the maximum value, and the sine wave is modulating that to turn it into an animation. If I got rid of that and just plugged this straight in, we go back to our mesh here, turn this on. Now you can see that I can directly control the position of the slide. So the next thing you might ask yourself is, okay, so I know that I can mask out which vertices to move using this bit mask. I can tell it what direction to move, right? And I could have actually baked this vector into the vertex colors, right? I could take that group of vertices that I've identified as a slide, and I could give them the red vertex color, and that would give them this vector. And then I wouldn't need to define that vector in the engine. The reason I've done it this way is that this gives you 3 more channels of vertex data to use. What if you have other ideas for how you want to use that vertex data, right? Maybe you want to put in a curvature map for wear and tear, or anything like that. So this just, by putting that data in the shader, frees up the vertex color channel, and it's pretty simple to keep track of that number. All right, so once you have this vector, we're just taking it out into the world position, and we're adding it to any other masked positions that we need to do. And so translating or transforming laterally, right? So moving in the vertices X, Y, Z is very simple. All you have to do is mask the area and then multiply that by a vector of your choice, right? So I want this to move in one direction. That's very simple. You could potentially do this with traditional Vertex animation textures, right? So Vertex animation texture is a texture that rather than using a parameter, and this you could use a material parameter collection and animate it with a curve or anything like that. But you can also take a texture and have that texture be sampled, and the value on any given pixel of the texture represents one frame of animation. And I'll be putting in a link to a really great article that goes over in extensive detail Vertex animation textures and how you can use them, and I'd highly recommend taking a look at that. But I wanted to keep this more general, right? So just showing that a value is being read. It doesn't matter where this value comes from. This value could be read from a texture that is baked from an animation that's been hand authored. This could be made mathematically, like for example here with a sine wave. You can use really anything to drive this animation. So moving on, the next topic is going to be rotation. So rotation is a little bit more complicated. When we look at both the hammer and the trigger, these are animations that require rotation. So rather than just multiplying by a vector, we need the rotate about axis node. There's also a rotate about axis cheap node, but I found that in its current form, the y-axis is broken on it, and that's what I needed for my example here for the way that my hammer and trigger are rotating, and I didn't feel like fixing the material. So I'll just be using the normal rotate about axis. So you have to use this node, and this takes a couple of pieces of information here. So once again, we've filtered out, we've masked out anything that isn't our hammer, and we're taking that and we are putting it into a multiplication with this rotate about axis. And the rotation axis is y, or green here. So this is going into the normalized rotation axis. The rotation angle is going to tell us how much do you want to rotate, right? And so in this case, I've just got that being driven by a sine wave, but just like before, you could have that driven by a Vertex animation texture. You can have that driven by anything, right? Then we have the pivot point, which the pivot point is by default, right, it's going to be the center of the mesh. And we don't want the mesh, we don't want this to rotate around the center of the mesh. We want it to rotate around some point in space. So if we go back to Blender here and we look at our mesh, I'm going to go into the side view. If we go ahead and add in an empty, there's a lot of different ways that you can figure this out here, but I'm just going to hover this empty vaguely around the area where I want this to rotate from, right? So it's somewhere around here, right? And so we can see here, this is negative 0.83 and 0.37 within Blender. So if I go back over to Unreal, you can see that I have this set to negative 86 and 30. So roughly the similar position, right? You can copy it exactly. I fine-tuned it to a spot that I liked that rotation. And the reason that it's 86 instead of 0.86 is just because of the scale difference in Blender and Unreal. But once again, what you could have done, you could have determined that in Blender, and you could have baked that rotation axis, that pivot point, into the RGB value of the vertex colors, and then you can just read the RGB and use that for your pivot point. So again, I just chose to keep those RGB values free for the sake of demonstrating this all within the shader. Then you have your position, which is just the world position of the mesh. The other thing that you need to do with rotation is you have to fix the normals. And the reason for this is when you're when you're translating or transforming a a polygon forward, backwards, left, and right without rotating it, the normals of the mesh stay pointed in the same direction, right? If I slide something on a table to the left, up on that is still facing up. But if I turn it on its side, I rotate it, what used to be facing up is now facing to a side, right? Maybe it's facing towards yourself or away from yourself, right? Depending on which way you decided to rotate that object. And Unreal doesn't know that. It's going to continue to have that side face, that used to be the top. It'll have its normals facing upwards still, and the shading will be completely wrong. So what you need to do is take this node, fixed rotate about axis normals, and give it the rotation axis, which is the same as before, just our Y rotation axis. We feed it the same angle as before, and then this will give us a new normal. And I've just taken that normal and masked out the certain parts of that normal, because I'm going to be recombining it with another corrected normal later, right? So I wanted to correct it for both the hammer and the trigger and then combine those corrected normals. So essentially I'm saying, okay, well, this I only want to be the normals from, say, the hammer, and how that's being corrected, and get rid of the rest. And you can use that with the movement mask here. So this is going to apply the movement only to the hammer, while the rest it stays the same. And then I'm further actually masking it out so that I can add in this next one here. And so it gets a little bit more complicated if you have multiple different pieces that can independently rotate. And you want to make sure that you're compensating the normal directions for both of them, or else your shading will be wrong. So basically that's what this section's designed to do. Hopefully that's detailed enough, but just keep in mind that you have to correct that. And the way that you would correct that would really depend on your specific application. So I don't want to get too in detail about what I've done here, because it might not really be relevant for most use cases. But essentially, again, I'm correcting the normals, masking out the parts of the normals that I'm not using, and combining that with another normal map that is also corrected and masked out. And then that's just going into the actual normal here. And so that all makes sense. So there's a bit more going on with these, because you need to use this rotate about axis node, and you need to correct your normals. But that's really about it, right? And so if you're using Vertex animation textures, you don't necessarily need to go through all of this. But what this in particular is doing is it's decoupling the Vertex animation from the poly count. One thing you're going to run into with Vertex animation textures, unless you plan and prepare accordingly, is that a texture in Unreal Engine can only be 8K at a maximum. And so with a vertex animation, that means that if you're animating each vertex independently, you can only have 8,000 vertices in a mesh. So what we've done here is, rather than trying to animate each vertex independently, we have taken those and made elements, larger features that are going to be animated together, right? The slide doesn't need to stretch, so it doesn't need to have some vertices being controlled differently than other vertices. They all should be moved a uniform amount, right? And you can do this with other types of complicated objects too, like a human. The arm, as it rotates, the forearm is all the polygons that are in the forearm are going to move together, generally speaking, especially if you're looking at a distant person, where you're not going to notice the tiny changes that you would see when they're up close using a skeletal animation, right? All of those polygons will move together as a group. So you really want to assign them the same value and move them as a unit. And that gives you a lot more options and allows you to look at much higher poly count meshes to use this treatment on. And so again, in this particular case, I could animate this using curves. I could animate this using math. I could animate this using textures. But at no point did I ever have to use a bone. And that's the real key takeaway, right? Most of you are already using Vertex animations in your foliage. You would never make a tree or a blade of grass or a bush and then put a skeleton in it and then animate each leaf by hand, right? It just doesn't make sense. So this is ultimately going to allow you to achieve animations that will rival skeletal animations without ever having to take the performance hit. So hopefully you find this insightful and have ways that you can apply this. If you have any questions, feel free to throw them down in the comments section. Once again, this has been kind of a surprise. I just recently hit 100 subscribers and 10,000 viewers on my channel for something that is just kind of a hobby that I do in my free time. I never really expected it to get so much traction. So thank you all so much for watching, and until next time.